Hello everyone, my name is Mohamed Kassem. I'm the co-founder and CTO of eFabless. And this one is going to be a presentation on the lighter side. So it's less technical than what you've seen in the conference so far, or the event so far. So I wanted to, the title makes a point for what's to come, and you've probably seen a glimpse of that over time from the exchanges with the team here, including the team from Google. So I wanted to show, what is, how possible it is. I want to remove the enigma that it is very expensive, it's prohibitive to think about an ASIC and design an ASIC. So this is something that historically is left to the high volume designs. I come from, my background is Texas Instruments, so I used to work with Texas Instruments wireless business unit. And in that business, everything's high volume, and it justifies the need for actually customizing the ASICs. As a matter of fact, I believe the world, we customized everything to get to the phone. Now the world is coming back. We need to divide that phone up into pieces and make it at the edge. Different sensors, different things. So it is actually very interesting to see how the need for customization will arise. So eFabless is a company that is based on a community model. But it delivers chips. So the output of the company is chips for systems, for products. It serves different markets. So in a variety of markets that custom ASIC will serve. And we look at it this way. So everybody calls this the long tail, which is the many products that have low volume. And typically, the volume and the revenue of these products is too small to justify an investment in the custom ASIC. So it doesn't work. And so you would have the whole range of the orange on the left, on the right-hand side here, very underserved in terms of what can be customized and available to the designers to make some decisions. We believe that if you enable the customization at the low volume, in an area where wasn't actually enabled, you will get a lot of value in the right size compute and power. You'll be able to optimize both the hardware and software and get to what you want exactly. This is a key part, the right size, compute power and cost. So people will say, why is a standard product not enough? Well, because it's not. It wasn't possible to actually, even if you look at groups or communities like the TinyML, for example, most of the hardware that's being used is standard hardware, and there's no customization around it. There's a lot of papers and a lot of intention, but it's not done in reality, in the physical world. So eFabless's job in the world, the way we want it to exist, is to simplify the process of making chips and make it available to more people that can actually do it. Similar to what happened in the app stores. What happened in the app stores, it's actually easy to say app stores, but the reality of the app stores were, before an app store, if you wanted to build a piece of software and sell it, you will need to find customers, you will need to find sorry.
I'm trying to fix it for whatever reason.
What's that?
I'm trying to fix it for whatever reason. It's cutting off on the left side.
Okay. So now it's on the other side. That's okay. So what happened is, now you have to go, if you wanted to make a software product, you have to find a customer, you have to find developers, you have to find, it's a big undertaking. The app stores created a business process, said, okay, here's what you need to do to make a product, and also I'm going to give you a stack to start from. You're not starting from zero, and it's a standardized stack. So that enabled millions of people, including kids, to actually do that. to make their own apps and put it in the marketplace. So if you think about it, the democratization aspect here is that enable putting an infrastructure or system that allows people to do these things. In the design world, it's semiconductors. It's a little bit more complicated. So kind of, that's what we want to do. We believe it's going to be open for a lot more people. And it's a little complicated to do it because it's not just one company owns one thing. So it's a bunch of things, at least these 6 components here, that if any one of them is not there, you can't make a chip that is going to the market. So, and this is very clear, is that I wanted to actually, the output of eFabless is going to be our real chips that go into products. So you need to know what the market needs. You need to collaborate with other people because you don't know all the experiences around you for building a chip. You need IP, you need the tools, access to foundry PDK, and an affordable manufacturing and test. This is very important. Now, in the world, there are partial solutions that exist to solve for academic applications or just very tiny, it will be restricted around certain processes and they don't have that commercialization aspect available. So you would actually use it and get some silicon and you want to convert it to a chip. So we wanted to start from a clean slate and do the whole thing from the beginning and then how we did that. So if you look at today's approach, this is just a picture that represents what's happening today, is that any organization that wants to build their own system for designing a chip, they have to go access the different providers of IP providers, EDA, process technologies from different places, and then each one of them has to have the right legal agreements, license agreements. And this is, to me, it's like a waste of human life, human time. If you actually think about it, the same process being represented or being done and everywhere. It's a waste of time for everybody involved in it. I have personal experiences with some of these things that are obviously probably the same, take months. So the number one thing that we did, this was early, like in 2015, we said, okay, we're going to use the cloud, but the cloud typically is associated with the compute. So elastic compute, surge compute. Well, guess what? Everything else about the cloud is actually very useful. So the ability to actually have secure environment, have partition collaboration rooms, firewalling across the cloud, having a centralized infrastructure where it's one maintenance, you can actually support it and maintain it. And you can have the compute elasticity as well. So there's no reason you can't have that. But the cloud enabled the ability to hide and subdivide the world into interesting ways that allow for collaboration. And one of the things we did to start with was obfuscating the PDK. So, and this is something that we did on eFabless specifically. So when you obfuscate the PDK, you get in without an NDA. You can use processes or PDKs that are not open source from specific foundries in the specialty space, mostly on the targeted towards a heavy analog mixed signal, like XFAB. And when we obfuscate the PDK, we hide the certain pieces of it and that don't impact how the designer works. So you can, for example, with a foundry like XFAB, and we agreed that we're going to hide the baseline and leave the back end, all the metal up, possibly open for these products. We also did that for IP. So when we started, as you can see, started with 180 nanometer. This was around 2015, 14, 15, and we did that with the IP. So we created chips that are actually open source, but the IP in them are not open source. So if you actually take a look at this chip is called Raven. It was developed with a RISC-V core. This is a P2R-B32, that's the infamous RISC-V core. And it was abstracted into black boxes, and for the ability to be somebody who can use it. I can show it to you and I can show it to you live, because we agreed with the foundry that, or the IP provider, that you don't have to see. Now here's the cloud. Very simple. I can hide the content of the design, and the actual IP is sitting somewhere else in a different place in the cloud. And then when I tape out, I merge them. So is that cloud? It's computer networking, really. But right now it's available in the cloud, so it makes it a lot more flexible to do. And so these are things that you can do. And we added the tools. So in the tools, this was a little tricky because we wanted to start. It's a big hurdle to start, actually, to be able to get the tools and the access to the licenses and even trial licenses. So what we did is that we said we're going to go all the way open source tools, and we took that. I personally went to travel around the world and took anything that worked by anyone in the open source space, a router, a placer, a simulator, and then we, this is I call it this collaboration from the village, big worldwide community, assembled an open source flow that actually can be used for analog mixed signal and digital with limitations, but you can instantly work with it. And just to give you a taste of that, since we have a little bit of time, so if I go to eFabless.com, and it's not advertised right here now, but if I log in to this platform, so we talked about the marketplace, for example. So there's an IP marketplace. Well, the IP marketplace looks a lot like other, excuse the screen because the resolution is just making it so big. Like other marketplaces, they have catalogs. The difference between these catalogs and this catalog is this IP actually exists on the platform. You can actually take it and put it and use it without an NDA, without a license agreement. How? Again, abstraction and obfuscation. It's protected, so it's not like the IP provider, is sacrificing that IP. We also have in the marketplace designs to start from. So the chip that I showed you, it's called Raven. So this is a 180 nanometer. It's available as a library component, actually. Okay, and I can take it and take a copy of this, okay, and then say. I created, this is my own, I'm logged into the platform, I want to start working, so I took an action, I'm going to move this to my workspace, okay? And then once it's moved, I go, I'll be able to go to my desktop, and then when I start the desktop, if it wasn't started already, this one started because I was doing something earlier today. But let me close everything because I have to close everything to get the screen proportionality right. So let's try this again with the resolution that we have in hand. So I open, and there's a project manager here. If I scroll down a little bit, I'll, where the Raven chip, I should find right before the S. Did I say press 5 to 10? Right here. Okay, so this chip has been actually cloned from a marketplace into my workspace. This is an open source tool set. This is Magic. And it is very obvious to see that it's abstracted, and then when I expand the hierarchy in this chip, what you'll see in a second is that it's happening now. So you'll see in a second, I don't really need, so in order to build a chip, people say, I want to see the I/O, what's in the I/O? I actually, no. Arguably, you don't need to see what's in the I/O. If the I/O is well developed, then it actually becomes a standard component. Unless you're actually working on a very complicated multi-domain mixed signal analog voltages, the IOs actually, you should be able to abstract them. So you can build a back frame very easily with an automated way. Here's the X, the big X, this is on the SRAM. The same thing, the SRAM is not actually even on this cloud. It is, you can use it, you can put it. This chip is available actually for anyone to actually look at the Verilog, look at the behavioral models around it, but if you want to tape it out, you can modify the Verilog and then redo it again. Yeah? So, and then for the analog world, for those who have like to look at the analog world, we have the ability to basically design transistor level, and then you get everything I've done here. Anyone in this team here can actually log in and do it without any NDAs or license agreements. And these are real technologies, real process. This is called 180 nanometer for big stack, for example. Okay? Then you can, when you create a project, you will be able to choose which technology. So these are the PDKs that are available, and automatically the system will recognize where you are, and it will configure the entire environment around that PDK. So this is just I want to give you an idea about how it actually works. We are a partnership with different companies. One of them is Synopsys. So Synopsys, imagine this entire environment will have Synopsys tools on it in a certain framework. And then I'll bring that back here. So going back to this, so we started with open source tools to enable that smoothness of access, that immediacy of access. And I showed you the marketplace, and that marketplace eventually it has IP from a foundry, it has IP from developers around the world, and it has some labels or certification that tags that show what's the state of the IP. So ideally, we want the company to look like this. There will be two models. One is that on the right-hand side, designers design their IP, digital, analog, or so, and they push it into the marketplace for others to use, and while obfuscated. On the other way around is that people who are building systems, like products like smartwatches or air purifiers, or they can request from the platform certain specifications, and the community will respond. And the word community here is inclusive of anybody that knows how to do design or contribution anywhere, of any sort. Meaning that if you're a software developer, that you want to contribute to develop the embedded software, so be it. So there are design request processes, and then the platform in its integrity, it looks like it has these features that can be used for design and also used for education. So you can have it's being used for teaching courses and labs with a real technology. So it is key that this is all integrated in one place, and you don't actually have any barriers until you actually tape out. You start having the question about who's how to register, how to actually get it done. I'll leave this. This is too many bullets, but the key part I would like to say that eFabless is the only company that provides something that gets you in less than 5 minutes into the real action. Okay, to do something useful. Today we're working with process technologies like 130 nanometer, 180 nanometer. From foundries like Global Foundries, Skywater, and XF, but we're on the way of getting more. The IP that's being used, like we have 2 ARM cores. I know this is a RISC-V forum, but just I'm using the ARM example here as an example of an IP that is not open, that can be instantiated and brought in and used without a license agreement, without an NDA. You can actually do that here. The alternative is to go to our ARM website, download it, get a license, sign a bunch of other things. You can't download it here, but you can actually put in a chip and use it to simulate your system, and then tape out with it. So we call that try before you buy. You can actually try something, and then obviously I'll talk about the low cost prototyping aspect. So examples of some of these chips that we did is, these are 4 chips that we did in the beginning with XFAB. The 2 on the left are RISC-V microcontrollers, 32-bit, and the 2 on the right, the top one is ARM, M0, and then the bottom right is an analog test chip. And then I just skipped through these. These are the block diagrams of the different things. The most important part of these chips, they're mixed of open source and closed source. So the RISC-V core here is open source. The rest of the chip, the IP, especially the light, the yellow greenish, these are closed. The chip itself is open source, so the hookup, the netlist of this chip is open source and it's available on GitHub. When you put it together and you push with eFabless, eFabless puts the guts of what's hidden and puts it to manufacture. So it's important to say that just by using the cloud and putting some rules around it, you can unshackle a lot of the traditional issues with access for tools and IP. Obviously, not every IP company is on board yet, but we understand why. So we try to walk with them and make them feel that address the concerns that they have. One of the things about open source chips that probably, and I say open source chips versus cores, because again, if you look around in the RISC-V world, there are so many people that are saying that there are open source RISC-V chips. No, they don't exist except with the Sky 130, since it started in 2020. The full chips, they didn't happen because there were the RISC-V core by itself is not a chip. It's a core. Okay? In order to actually have a production or a product, you need to have more and more peripherals and more sensor interfaces and other things that you can actually. So this was used in a security application because it was open source and it was used by NEC as a demonstrator for trust through transparency. And we all know what that means in terms of we've seen programs like OpenTitan from Google, etc. But this was an actual. NEC came to us and said, "I'd like to actually work with the Raven because it's a small enough chip that it can verify it doesn't have any Trojans." So it was a very interesting because we didn't market it as such, but they came and found us and talked about it. So all of these chips have been designed on 100% open source tools. Second part was to simplify the process is to actually take it down to the next level, which is the open source PDK. So we now that we have that platform, we knew that Skywater is seeing the opportunity in opening the PDK to allow for potentially more business. And at the same time, the stars aligned and the Google team got excited about it. So in partnership between eFabless, Google, and Skywater, the first PDK in the history of this industry to be open source that's fully manufacturable was the Sky 130. Just the background on this PDK, it is actually full. It is the one that is used by Infineon for the products. It's called the PSOC. So it has shipped billions and billions of units with it. It's a very robust process, been proven, and it's now made available for public use. But it is manufactured 100%. And then we later in 2022, through the results that Maxime did, Global Foundries got encouraged as well. So they opened a program. Again, that was sponsored by Google. And then the third foundry, which is on their own, opened one of their PDKs, IHP in Germany. So it's going to look like an avalanche. So because every foundry is going to ask themselves, why am I holding back a PDK if it's not protecting secrets? Because just to give you an idea, the Skywater PDK was downloaded roughly about 300 times a week, distinct downloads, for the last 3 years. So just imagine the number of people distinct, so this is not duplicate, that are interested in that. Now, are they all designing? I don't know. No, probably not. But it just gives you the larger number of just the pool and the probability of how many people can actually use this. And you've probably seen this in other presentations, or I don't remember the order, but the PDK went viral when it was released, and we had a large community around it. Now, one of the things we did around this was to actually create the open lane flow, which is you can treat it if you treat it as a compiler with some sacrifice on the PPAs, it allows software developers to actually. And I'll attribute that to our friends in Google, the team we're working with. They remember basically the statement is that I don't know what a DRC is, I don't know how to fix it, I don't want to see it. So if you take that in mind and say, okay, that's the priority, then you can make it a compiler, then as long as it finishes. One of the things we did also is use LiteX and Amaranth to generate some of the RTL. So to hook up with that flow. That flow takes you from RTL to GDS altogether. Some of the things that appeared as a part of this process is that one of our community leaders, his name is Matt Venn, created a system called Tiny Tapeout that actually allows kids to actually play and do a schematic like what's on the top left, and they save it after they simulate it, and then it gets dropped into a slot on a chip. They don't know what's happening, but except that they will get a board later and actually use it. We did this with analog and digital, and I want to emphasize here is that literally, now the fact that it's open source, it just doesn't have limits. You can talk about it, you can ask questions, you can share knowledge, you can improve it, whatever you need to do. So one of the most important things that we did is that actually create the Caravelle chip. This chip you'll find it on the book, at the back of the book, that it was actually, this is the platform chip, it's called Caravelle. This chip is a RISC-V microcontroller that the designers can drop their own designs in it. This is a fixed chip with a data sheet around it, and it's open source. And the way it works is that you can go clone it, add your own design, and if you see it on the book, you'll see that this is Shumpei would show that his design or their design is inside here, but the actual chip is outside. It's the Caravelle chip. Once a chip is made, they get a board. And that actually makes it a lot easier in terms of testing and wake up. And we have a couple examples here of, I will say, you're a physicist. I think for one of the projects, one of them is a physicist and a security software engineer. Two of them, they just got the chip wake up this morning. They designed it themselves, and they had I think it was a CPU. So.
They're going to be talking after you.
Okay, so the next talk, I guess. So, and then we provided additional boards and material to make it work. The most important aspect of delivering a chip that people rely on it is having very well verified and with coverage. This results is not actually verification. This is silicon validation. So we took all the verification that was. Wanted to cover and put it there, and applied it on the bench in an automated fashion. So then another thing is that actually enable a program like what happened with Google. So Google funded and sponsored open source shuttles. You may have already heard about that program, and that program ran about 9 shuttles. One of them is on Global Foundries. The popularity and the number of people that actually just jump in is huge, and it's been a very exciting journey. And there are some examples of this. I'll leave it in the presentation to click and go to eFabless.com/projects. You'll be able to see a lot of the open source projects that came out of this project. Now, eFabless actually created a product around this that is not open source. It's called ChipIgnite. So ChipIgnite, it's this is technical venue, but it's worth actually saying that with this type of structure of the cost, you can actually start an ASIC at as low as below $10,000 and get a 300 parts. And if you want to increase the volume, it's 20,000 for 1,000 units. So this actually shows you a data point that shows that I can actually get the first ASIC below the number of 10,000 for 300 units or 1,000 units for $20, which is something that wasn't possible in that world before. And it's not a shuttle, it's a full, I call it a house with electricity and plumbing, and then you bring in your finished appliances to get into that house. We have created multiple options for it, so some people wanted to use the features of the RISC-V microcontrollers, and some wanted to use the area in full. We're adding additional Synopsys and Cadence and Mentor tools in the future. Synopsys is the soonest, it's because there's an agreement on that, and it's going to be on the cloud to work with this. Now, we also wanted to, and I spoke about it on my presentation, in the course of the presentation, was actually to have the IP libraries available. So maybe just because of the demo, we'll just skip this one. So it's a ChipIgnite, it's $10,000. So we partnered with a couple of companies. One of them is called Cloud Supply and GroupBits, to create like a crowdfunding structure where someone can go put a picture of an idea, and then from that idea they can fund it, and people can pre-order it, and then you can fund your own project just through the idea. So just by putting a story. So we have this project called Clear, and it wasn't overfunded, it's overwhelmingly funded, but it was funded to the level where you can manufacture it and it's in the fab. And we wanted to prove that if you just have an idea, you don't need to wait for the Google shuttle or for the ChipIgnite money, you can just go crowdfund it. And that's something we've opened. Startups have been using our solution to try things. Big companies have been using it as well. And then universities have been using it significantly in courses and projects and research in different ways, especially with the fact that you can collaborate without an NDA whatsoever. We've had examples of this from on the left. This is a high school group that they taped out in April, 7 designs in the form of the tiny tape out, where they built little blocks, and these blocks have been put in the chip automatically. They will get a board, like Arduino. It's going to look to them like an Arduino board. You plug it in and work. We have on the very right-hand side, this is what's equivalent to, it's not equivalent to the technical college here, because this is a 2-year college, the community college of the United States, but the career path is different on the right-hand side, so we did the same. And in different cases, we simplified. The middle one is a university, and they use the entire environment in full. We have a class with Purdue, it's called STARS, it's actually running right now. It's 40 students that are coming undergrads, freshmen, just came out, finished the first year of engineering. They're designing their own different blocks, and they're putting them on the same chip. Cornell did the same. By the way, these people, every one of them did a different thing on their own. Like in Cornell, the professor chose to make a project team. Okay, raised the money from some university funds. In Purdue, it's a program supported by the industry. This is a MITRE and MIT Lincoln Labs. This is supported by the industry. We applied that, and that is an example. This is a result from designs coming from Stanford on the ED372 rather. Again, the students here, they designed their own project, and then I just wanted to give you, just look at the subtitles of the projects and see that this is a mix of undergrads and grads. It's very possible now that they can do it within the realm of a class, because the chip is mostly available, analog and digital. And then on the bottom left here, we use this is actually our poor man's characterization bench. It has a computer and a full 82 kits from Vigilant, and to do the full automation validation in Python. And there's some examples in the community. Some of it come from the Google shuttles, and some of them are coming from the ChipIgnite. it's amazing just to see how people who never designed chips before, okay? That's key. 60% of the people that got involved did not design chips before. They put something together and they made it work. And they learned from it. It's not the most industrious thing, but people get it and they get the experience of making silicon and testing it. There are some examples here that are very nicely put, and then I left in the slides different, just if you look at Twitter, you'll find a lot of applications or a lot of examples the community has around the world. And the key part is around the world. And if you haven't looked at the booth here for eFabless and Google, take a look at it. There's some of these chips and examples sitting there. What's missing in this, to make this actually superb, is actually getting the open source IP to be high quality. High quality meaning it should be used in a context of a product, no questions asked. There's a perception that the open source in general is risky. We have found that no, that's actually not true. If there's a spectrum, if you have a large enough pool that actually do work, there's a spectrum between very loosely done, useless, all the way to very high quality people who are investing their months of time to do something really they're proud of in full engineering. It's like, again, the apps, 99% probably, probably not, about 95% of the apps are useless, okay? But there is that, once you have a large number of them, you have that group that it has, thousands or millions actually, maybe, let's be careful, maybe thousands of apps that are heavily used as good applications that are reliable. So we want to incentivize the community and stay tuned to see programs that are coming from eFabless around building this and for different markets. And then this is one thing I would call is like, as you develop open source IP, raise the bar. Raise the bar, because if you raise it, it's monetizable and it's yours. So this has never happened in this history, is that you can actually develop something, let's say a RISC-V core. And it doesn't have to be open source, by the way, and it can be used and monetized in the library of IP that is usable in the marketplace. And thank you. I don't think we have time for questions.
その時間ありますでしょうか。あります。ありがとうございます。There's time for questions. There's time for questions.
Any questions?
ご質問ありませんか。よろしいですか。
Do you have any Japanese customer requirements?
No. So the question is that are there any Japanese customers? The answer is no. In Japan.
Someone Jasa is working on our.
What's that?
Jasa is working.
Oh, so actually, I have to take that back. This is Japanese. I don't know. I haven't seen the book until today, so yeah. So excuse my recollection of that. So it's not a customer. I call it. It's a fellow traveler that built something that is very useful for the community to be using. And we met some very great examples of potential customers here in the last few days.
ヒロテックのクリスと申します。テイクアウトしてからだいたいチップ受け取るのでどれぐらいかかるんですか？
From tape out, how much time does it take to get to the actual chip?
So to get to the board, it's 4.5 months. So from tape out to the board. So, and that includes, obviously the packaging and everything. So it's not apples to apples with the standard cycle time of a foundry, because that includes the full board.
ありがとうございました。これなければもうちょうど時間なので、これで終わりにしたいと思います。再び感謝の拍手を。
Thank you very much.